Hi, today we're taking a look through A-Level Maths, Core P1, Chapter 7, Linear Transformations. So this is basically the second half of matrices, which we'll look at now. The main thing this chapter is basically telling you is that all matrices perform some sort of transformation or multiple transformations. Okay, let's get started with the basics. So first thing is how we define linear transformation and some also basic definitions you need to know. So any linear transformation must have two properties. It must transform the origin to itself, so the origin can't move to a new position, and it must only include linear terms. So no x squared, no y squared, no xy's, or anything like that. We also have invariant lines and points. These are lines and points which are unaffected by transformation. Okay, so points that don't move when you transform it. So for an example, this will always include the origin, because I've just said in point 1, the origin must transform to itself, so therefore it's unaffected, which means it's invariant. Okay, next thing we're looking at is how we can define a transformation. So the way we define each transformation is we look at the effect it will have on 1, 0 and 0, 1. In essence, the unit square comprised of these 4 points. We know this point isn't going to move, so we're going to see where these 2 points move to, and 1, 1 will just be the combination of those two movements added together. So if you've got any transformation matrix A, B, C, D, 1, 0 will go to AC, and 0, 1 will go to BD. If you ask the maths for this, so say I want to transform the point 1, 0, to work it out, remember, you have to write that as a column vector. So you'd have to do A, B, C, D times 1, 0. It always goes after the matrix, and it goes vertical as a column vector. And if you work it out, this gives you AC, which then gives you the point AC. Okay, let's see some basic examples. We're going to start looking at reflections and rotations. So I've got this matrix here, minus 1, 0, 0, 1. So I know 1, 0 is going to go to the first column here. So it's going to go to minus 1, 0, which means this coordinate is going to move over here. Okay, and sometimes I do little arrows, just so it sort of helps you visualise what's going on. And into the second half, 0, 1 will go to the second column here. So 0, 1 goes to 0, 1. So it's invariant, it doesn't move. That means this point stays the same. And we can also include 1, 1 if you want to. If you do include that point, that will go to minus 1, 1. So it's just basically these two coordinates added together. So hopefully what you've seen here is we've got a reflection. Here we've got a reflection in this line, which is why 0, 1 didn't move. So you would define this transformation as a reflection in the y-axis, which again is the same thing as the line x equals 0. Okay. Next, we've got another matrix here. We've got the matrix 0, 1, 1, 0. So basically identity matrix, but with the 1s and 0s switched around. So we do the same thing. 1, 0 is going to go to this first column here, which is 0, 1. And 0, 1 will go to the second column, which reads 1, 0. So actually what you've got here is these 2 points are swapping position. Okay. So hopefully from there you can see what's going on. You can also work out 1, 1. If you work out 1, 1, it turns out to be invariant. It stays at 1, 1. And that's because this matrix represents a reflection in this line. So after you've done a few of these, it becomes a bit more second nature spotting exactly what's gone on. But you've done enough reflections, rotations and stuff from GCSEs, this shouldn't be too hard. So to define it, we're going to say it's reflection. And this is in the line y equals x. Okay, other type of question to ask for is it'll give you a reflection it wants. So in this case, reflection in the line y equals minus x, and it wants you to define that matrix. And they should basically do the exact same way, except we're going to work backwards the entire time. So first thing, let's get our line. 1, 0, I want that to go to 0, minus 1, and 0, 1, I want to go to minus 1, 0. So we started off with basically these two coordinates, where this is my coordinate 1, 0, this is my coordinate 0, 1, because 1, 0 has moved to 0, minus 1. I have a 0, minus 1 here. And 0, 1 has moved to minus 1, 0. So I have a minus 1, 0 here. And that's it. This matrix will cause reflection in the line y equals minus x. And this kind of method works for any sort of question where it wants you to say, here's a thing, now define it in a matrix. Okay, that's reflections. That's probably the easiest section of all of this. We now got rotations. And this is quite nice because basically all the hard work or hard maths you need to do is pretty much given to you in the formula book. So here you've got the rotation. Here you've got this formula here, this matrix, which is a rotation matrix. And you were given that, and that'll rotate it by theta degrees anti-clockwise about the origin. So let's go for a quick example. Here I've got this matrix, and I want to say what transformation does it represent. This will just be a rotation. What will make it slightly easier to see is if I take this half into the matrix. Doing that, we've now got this matrix, which hopefully you recognise as like the exact trig values for sine 30, cos 30, sine 60, cos 60, etc, etc. So it's going to be one of those. So let's have a look at a couple of them. Looking at my top left entry, this one here, I know that cos theta wants to be root 3 over 2. Okay, and this has one of two solutions. Either theta can be 30 degrees, because cos of 30 is root 3 over 2. And we've also got theta could be 330 degrees. And it's going to be one of those two. We can work out which one of those two it's going to be by looking at a sine coordinate. So here, if I look over here, I know that minus sine theta is going to equal a half. Or more simply, sine theta will be minus a half. And you want to see which one of those two it satisfies. So you should know that sine 30 is a half, which means it's not going to be this angle, which means therefore the angle that rotation represents is 330 degrees. So this is basically doing some inverse trigs with the calculator and a bit of recognising, a bit of sort of clever things, and it helps if you know the cos and sine graphs as well. Okay, another typical type of question. Here I've got another rotation, I think it's the same rotation. And I want to know where the coordinate 2, 0 will be transformed to from this matrix. And again, I said earlier, you've got to make sure your transformation matrix is at the front. And you write your coordinate as a column vector. Then we just work it out. I'll ignore the half until the end. Root 3 times 2. I can just write that as 2 root 3. 1 times nothing, and I've got minus 1 times 2, and root 3 times nothing. And taking the half in now, that there is my answer. So the coordinate 2, 0 got transformed to the coordinate root 3 minus 1. Okay, that was reflections and rotations. Now we can look at enlargements and stretches. And again, these aren't too bad. So this is your basic enlargement. So here I've got the enlargement 2002. You should recognise this as two lots of the identity matrix. So it's no surprise it makes everything twice as big. This is going to be an enlargement by a scale factor of 2. You see a quick sketch here, and you see basically the whole triangle is getting twice as big. The key question here is how much bigger will the area get? So here we have an enlargement of a scale factor 2. That is basically your length scale factor. And if you want to work out the area scale factor, it is your length scale factor squared. So the area gets bigger by 2 squared, so the area gets 4 times as big. That's basically because the length has got twice as big, and so is the height. To work this out even quicker, the area will get bigger by the determinant of this matrix. If you work out the determinant of this, this gives you 4. And this is always true, and this is super useful. And it's a really common question to sort of ask a question based on area. We have to work it out by finding the determinant of some sort of transformation matrix. Okay, we've got some other stretches and stuff to do. So all of these basically are modified versions of the identity matrix here. If you just change one number, it will only affect it in one dimension. So 3, 0, 0, 1, all that will do is shift my 1, 0 up until 3, 0. And of course 1, 1 will go to 3, 1. And what you've got here, these 2 points won't change. So this is going to be a stretch of scale factor 3 in the x direction. You must specify which direction you're being stretched in. We can also extend this idea where you've got two different numbers here and here. So this one's fairly obvious. This 3, 0 part will stretch in the x direction, and this 0, 2 will stretch up in the y direction. So basically this square will move to this bigger rectangle. And if you wanted to define that, you have to define each stretch separately. So you'd say a stretch of scale factor 3 in the x direction, and then the same thing again, but now it's a stretch of scale factor 2, and now it's in the y direction. Okay? So, for any linear transformation, like I just said, we can use a determinant to represent this area scale factor. So here I've got this matrix. I don't know exactly what it does, but I can work out how much bigger it will make any shape. So if I work out a determinant, that comes out at being minus 10. No, it comes out being plus 10. You have 2 minus minus 8, which is 10. That means it will make the shape 10 times bigger. If the determinant was minus 10, it would still make the shape 10 times bigger, but basically it goes inside out. It's like a negative scale factor. As it gets bigger, it just sort of goes inside out in the process of it. And lastly on this topic, from the last video matrices, I said you have a determinant of 0, which makes the matrix singular. And again, we saw that basically moves some points onto the same line. And you can kind of see that will then make the shape have no area. Just sort of tying that bow there. Okay, I'm just going to finish this section with a typical exam style question. So we've got a matrix given by this matrix here. Part A, describe Fourier transformation represented by M. I already did that. That was a stretch scale factor 3 in the x direction, scale factor 2 in the y direction. Now part B, this is a little different and can throw you if you're not used to it. We then have a triangle with these vertices or points, and we want to find the area of that triangle. Best way to do it is sketch it out, and you kind of see that they always give you triangles that you can work out using half base times height really easily. So 2, 2 will be here. 8, 2 is going to be along that same line. It's still 2 squares up. And we've then got 3, 7, so 3 squares along and 7 squares up. Now this is a nice triangle because I can work out the base and height really easily. The base will be from here to here, and the height will be from here to here. So the base going across from 2 to 8 will equal 6. The height, I go up from 2 up till 7, so my height is 5. So therefore the area is going to be half of 6 times 5, which is 15. We now have a triangle is transformed by this matrix, so I have 3 new points, and we now want to work out the area of the new triangle. So this area will just be the old area times by the determinant of that transformation matrix. So the determinant of 3002 will just be 6, so that will equal 15 times 6, which means my new triangle will have an area of 90. Occasionally just say 90 square units because you're not told are things centimetres, millimetres, etc. So that was enlargements. Last thing to do with the linear transformations is you can have successive transformations. This basically we've got 1, 2 or even more transformations all merged together into one big matrix. So the basic idea is, say I want to do an enlargement of scale factor 3 and a rotation by 210 degrees. I could do that in one single matrix just by timesing those two matrices together. And for this question, it doesn't matter which order you times those together actually. Either way, doing that, you would get this combined transformation matrix. So questions basically fall into two main categories. You've got this side where you combine them yourself, or the more common side is where you're given some matrix, you're told what it represents. So here an enlargement and a rotation. And you want to basically tease apart those points to work out what enlargement and what rotation. The best place to start is going to be with the enlargement. So you've got enlargement scale factor k. You can always work that out by taking the determinant. So if I swing back a slide and we looked at the first enlargement, we noticed that the matrix 2002 had a determinant of 4. So that means if the determinant is 4, the scale factor is going to be 2. So we're going to work out the determinant and then we're going to square root it, and that will give me my enlargement scale factor. So let's go for this one straight away. So the determinant of this matrix will equal 2 root 3 times 2 root 3. That is going to be the same as 4 times 3, which is 12, minus, and I've then got 6 times minus 6. So 12 minus minus 36. So here this determinant is going to be 48. That's not my enlargement scale factor. So my scale factor is going to be the square root of 48. And because there's so many root 3's in here, I'm going to write this in simplified third form. So for 48, 4 goes into it. So this is the square root of 4 times the square root of 12. 4 goes into 12 again. So I've got root 4 times root 4 times root 3. Square root of 4 is just 2. So those two 2's times together gives me 4 root 3. And that's my scale factor. That means because I've got this enlargement, I can now work out my enlargement matrix. So this is 1/2 of it. The enlargement matrix must have looked like this. It's going to be like 1001, but instead we're going to have 4 root 3 in place of those 1's. Now we can combine these together. If I basically divide the 4 root 3 out of each term, I'm going to be left with just the rotation. Okay? So what I'm doing there, if I have any matrix, and if I say times it by 2002, that will double all my entries. So because in this case I'm timesing it by 4 root 3, 4 root 3, it's going to multiply all those entries by 4 root 3. So I can divide that out, and I'm now going to be left with 1/2 and 1/2. Here, slightly harder, I've got 6 over 4 root 3 and minus 6 over 4 root 3. And again, we can simplify these as well. So to simplify these, we have to rationalise my denominators. So again, you have to make sure either calculator works really well or you're okay with this basic level of GCSE maths. Rationalise the denominator, I've now got 6 root 3 over 4 times 3, and the minus of that over here. 6 and 3 cancels down into just 2, and 2 and 4 cancels down. So I've got root 3 over 2, which means here I'll have minus root 3 over 2. Okay, and keep in mind most calculators will do this jump for you straight away, going from there to there. Okay, this looks very familiar to rotation we saw earlier. This is going to be rotation by something like 30 or 60 degrees. So I know that cos 30 and sine 30 are both goes like half and root 3's over 2's. Let's work it out. Let me just grab this over here. So we know that cos theta is going to be 1/2, and we know that sine theta is going to be minus root 3 over 2. What I've done there, I've just compared these two entries to these two entries. If cos theta is 1/2, I have two options. Theta could be 60 or theta could be 300. You then plug both of those into this one. So you work out sine of 60. That gives you root 3 over 2. That's not working, which means your answer must have been theta is 300. So now I can finally answer the question. value of k was my enlargement. That was 4 root 3. And my rotation by theta degrees, theta was 300. So slightly more hard work to do here, but there's nothing too crazy right now. Just make sure your first step is always be to work out the determinant, and that'll give you an enlargement scale factor once you square root it. Okay, now looking at linear transformations in 3 dimensions. This gets super complicated super quickly, so they've made it a really short chapter. What we would do is remember a few things. So to remember reflections in the planes x equals 0, y equals 0, and z equals 0. Those are pretty straightforward. All you need to do is remember the identity matrix, and you're just going to alter the coordinate that represents the x, y, or z coordinate. So for each of these, you basically start with 1, 0, the 3 by 3 identity matrix. For x equals 0, you change this 1 to a minus 1. For y equals 0, you would change this 1 to a minus 1. And for z equals 0, you would change this 1 to a minus 1. Okay, you're not given any of these, you have to remember them, but they are all fairly straightforward. Okay, that's reflections done. Next, you've got rotations, and you can rotate by the x-axis, y-axis, z-axis. All this comes from the normal 2 by 2 rotations. So for that, it was cos theta minus sine cos. So to rotate by the x-axis, that means you do not change the x-axis, and you basically just copy this in to give you that rotation. So to rotate about the x-axis, the x values don't change, and the y and z stuff changes to your normal 2 by 2 rotation. So that was x. Z looks exactly the same. I'll come back to y in a second. Z, this will be 0, 0, 0, 0, 1, and this would then be cos, sine, minus sine and cos. Okay. For y, we do the same thing. We're going to have this sort of cross in the middle. And where I remember it is you basically want to put in this 2 by 2 here. You want to write cos theta, sine theta, minus sine theta, cos theta. And any case, anything you write basically falls outside the matrix, like this sine theta, you just wrap it back around. So it goes here, this fell out the bottom, so we wrap it back around to the top. And this fell out the bottom corner, so it goes into the top corner. Okay. To me, that makes the most sense. In case you're interested, that sort of wrapping around trick also explains why you have this matrix of alternating signs. You're basically doing the same thing there, but I won't delve into it here. So they're your 3 rotation matrices. Again, you have to remember all of them, but remember they're all based upon the 2 by 2 rotation matrices. If an exam question on this, it'll basically either be writing down a represented matrix in terms of transformations. So write down a matrix that would represent a rotation of 60 degrees about the y-axis, or applying transformations to points. So here's this transformation matrix, apply it to the point 2, 0, minus 1. Okay, I haven't seen anything that's anything besides that type of question. Okay, last thing for this chapter, we have the inverse of a linear transformation. This one's fairly straightforward and could almost belong in the previous chapter. The basis of it, if you have an inverse matrix, that represents the inverse transformation. So if you want to invert this matrix, we can do that. It's going to be 1 over the determinant, which is 16. These two swap places and these two swap signs. So it'll be this matrix, and if you take that 1 over 16 in, it gives you this, and you can see fairly obviously that that's going to be the inverse matrix. That'll do the opposite transformation. This will enlarge it, this will shrink it back down again. Okay, we can do it for any matrix basically. So here we have the matrix from before, 0, 1, 1, 0, which was the reflection line y equals x. And again, we can invert this matrix, and that'll give us the inverse transformation. So 1 over the determinant, If we do AD minus BC, that's nothing minus 1. These two swap places, these two swap signs. And if I take this 1 over minus 1 into it, this actually gives me the same matrix I started with. So we have a special name for this. This matrix is a self-inverse. It's its own inverse. And what it basically means is you undo this reflection by performing it again, which makes sense. If you reflect twice, you're back to where you started with. And it's fairly common you'll be asked a question along those lines. Okay. Normally they'll say it, if they call this transformation matrix T, they will say show that T squared equals I, and that's the same thing as showing it's a self-inverse because you performed it twice and got back to where you started with. So this here is the same thing as saying that T is T to the minus 1. Okay, that also comes up quite a lot in exams, so it's worth at least being vaguely aware of that. Last thing, I'll just go through a standard exam question. Okay, so here we've got a matrix which represents a transformation T. Then you're typically given a point with coordinates x, y, and it's been transformed by this matrix M to give me a new point, 11, 15. And we want to find the coordinate of P, which is my initial x, y. You typically want to do this by matrix inversion. Sometimes they will explicitly say you must solve this by doing a matrix inversion. Anyway, let's get on with it. So I've got this matrix. I've transformed x, y. Remember, any coordinate goes into a column vector, and that equals 11, 15. And again, now this is just solving a typical equation from the previous chapter. So x, y will equal the inverse of this matrix. Again, always put it at the front, times by 11, 15. We can now work out this inverse. So the determinant, I've got minus 2, minus 6, which gives me 1 over minus 8. These two swap places, and these two swap signs. Okay, let's work it out, and as always, leave the factor until right at the end. So minus 1 times 11 is minus 11, minus 3 times 45 is minus 45, so we've got minus 11, take away 45, which gives us minus 56. Here we've got minus 2 times 11, so minus 22, plus 30, which gives me positive 8. Then we can multiply this 1 over minus 8 into it. So I want to divide it by 8 and flip the signs. It gives me 7 minus 1. So therefore xy equals 7 minus 1. Now for part B, slightly more involved. We have another matrix called N, which represents the transformation U, given that the transformation of T from the initial matrix followed by a transformation of U is equivalent to rotation of 180 degrees about the origin, and therefore work out the matrix N, which gave us this transformation U. Again, let us here get a wee bit messy, but just do it the best you can. First things first, we need to work out what this matrix is going to be. So we want a rotation of 180 degrees. That is going to be cos 180 minus sine 180, sine 180 and cos 180. So sine 180 is going to be 0, and cos 180 is minus 1. So this matrix here will be my rotation of 180 degrees. Now we have to realise which matrix transformation we perform first, and we do the transformation T first. So that means in a confusing case, that transformation T will come second. I'll explain why quickly. Whoops. So basically, we're going to have two matrices, and it's going to be the matrix M, because transformation goes first, that will go closest. The reason is if you have a coordinate x, y here, you will do this matrix times this first. So you perform that transformation first. Okay? So just remember it gets a bit switched around there. And we then have this matrix, which I think was just called matrix N. And we know that this must equal this rotation matrix. Okay, so be a rotation matrix times by xy. Again, here you don't need xy. I just concluded to make sense of why this matrix here went first, or went last, because you want to perform it first. Now we're left with this equation. And this equation is not too bad. This we can solve the exact same way we solved part A. We're going to do a matrix inversion. So here, this matrix is on the outside, it's on the right hand side. So that means the matrix N will equal this. And because it was on my right hand side here, the inverse matrix must also be on the right hand side. To the -1, this matrix we inverted in part A, so let me just copy it across, that's over here. I'll take the 1 over -8 out at the front. -1, -3, -2, 2. And then to work out n, you would just times those two matrices together. Okay, this one's fairly straightforward because this is such a nice matrix to work with. So it would be 1, 3, 2, -2. And feel free to check those numbers. So again, all they consider was -1, 0, 0, -1. You can just flip all the signs around if you're that bit quicker. Yeah, and I think you're fine leaving it like that. Occasionally might ask for it in a specific form, but unless they do, you can just leave it in that form. Okay, that was a lot to go through. Hope that made sense, and hopefully the exam questions helped you. So thanks for listening, and good luck.